impressed by the vertical takeoff capability of fighter aircraft. This is a technological achievement that the military countries around the world aspire to possess because it brings superior strategic advantages on the battlefield. Recently, a topic that has attracted attention in the military world is the aircraft carrier video. Today, ours will partly address this aspect, bring an interesting perspective on the combination of aircraft fighters and aircraft carriers. Welcome to Global New Military Updates. This is where military developments, global strategy, and modern weapons power are updated with a deep and emotional personal perspective. Each video is a beat of the times, where we analyze and reflect on power, war, and peace in a turbulent world. Ladies and gentlemen, don't take your eyes off the screen, and don't forget to subscribe to the channel, as well as leave a comment below. Surely you all know about F-35B, for the fifth-generation fighter of the U.S. First impression of it is the outstanding advancement. Thanks to the ability to take off and vertical landing, F-35B has become the world's leading modern combat platform. Vertical takeoff fighter has completely changed the military war situation, opening up new possibilities in combat. A prominent example is Japan. After ordering 105 F-35A from 2011, they quickly approved 42 more F-35B in 2019. With F-35B, the Japanese destroyer Izumo was upgraded to a light aircraft carrier, bringing the naval power of the Japan Maritime Defense Force to a new level. So, what are the strengths of vertical takeoff aircraft F-35B? How to take off vertically? Why F-35B's mass production while placing 141 though, one's full potential did not achieve that? Do vertical takeoff aircraft have strong development prospects in the future? Currently in the world, some countries equipped vertical takeoff fighters, not many. Some, like U-used Harrier II 2010, now switched F-35B. On the ship, Hasm's Queen Elizabeth. The Soviet Union has Armor 38, stopped in 1991, and Armor 141 did not pass the test. The USA leads with F-35B. In addition, I think Japan is also deploying this variant. The reason vertical takeoff fighters are few is because of complex technology, high cost, and payload-limited range compared to conventional fixed-wing aircraft. However, the biggest advantage of vertical takeoff fighters is the ability to take off immediately, while other aircraft are still accelerating. On the road, ICE's F-35B was able to fly, bringing advantages such as speed and efficiency in emergency situations, in wars like the Soviet War, attack on Pearl Harbor, or the conflicts in the Middle East and Gulf. One thing that is easy to see is that aircraft and runways are always targets. Just destroy a fixed aircraft and that plane is considered out of the war. But with the appearance of vertical takeoff aircraft, this has completely changed. Aircraft that do not need a runway can still take off quickly and be ready to counterattack immediately. Another advantage of vertical takeoff aircraft is the ability to operate effectively on aircraft carriers. You can imagine that with the limited space of the deck, the number of aircraft that aircraft carriers can carry will be limited. However, if using vertical takeoff aircraft, aircraft carriers can carry more aircraft per aircraft. Additional will create an additional chance of victory. In addition, vertical takeoff aircraft have advantages that require lower takeoff and landing conditions. During the Foglands War, he deployed Hercules on temporary converted cargo ships. This helped to compensate for the lack of aircraft carriers. However, although vertical takeoff aircraft have many advantages, they are not without their drawbacks. Their biggest weakness is their limited payload. Although vertical takeoff eliminates taxiing, and taxiing this requires the aircraft to be lighter. For example, the Harrier, when taking off vertically, has a takeoff weight of 8,695 kilograms, while when taking off normally it can be up to 14,661 kilograms. This weight deficit limits the aircraft to carry weapons and affects its combat effectiveness. In addition to the payload problem, another disadvantage of vertical takeoff aircraft is that the structure is more complex than that of a conventional fixed-wing aircraft. This leads to higher maintenance and repair costs and reduces the reliability of the aircraft, which increases the rate of hidden failures. Despite the F-35B with its superior performance or its exhaust system with its novel design, technical unreliability is always a concern for these advanced equipment. Especially the high crash rate of the F-35B has created a lot of doubts and controversies. However, despite these problems, we still have to accept its use. Let's find out how the F-35B performs vertical takeoff and landing. Then we will explore its short takeoff capability on a ship aircraft carrier. The most impressive point of the F-35B is its ability to maintain a hovering state, making it an ideal aircraft for the Navy, especially on ships without a long runway. The F-35B possesses many advanced technologies to perform vertical takeoff and landing, as well as short takeoff. To do this, the F-35B uses a main engine exhaust can to adjust direction, combined with a lift fan and auxiliary exhausts to provide the necessary thrust. Specifically, the propulsion system includes a main exhaust at the rear of the fuselage. The aircraft can rotate up to 95 degrees to divert thrust from horizontal to vertical, generating about 20,000 pounds of lift. A lift fan behind the cockpit, providing about 20,000 additional lift. Floats and 2 auxiliary outlets under the wings, each providing about 1,950 thrust. Floats to adjust the balance and attitude when the aircraft is in a vertical position. The key to the F-35B's vertical takeoff and landing is the ability to rotate the main exhaust in conjunction with the lift fan. This lift fan, with a diameter of 1.27 meters, is connected to the main engine via a drive shaft and a clutch. When it is in operation, it draws air from the top of the aircraft and pushes it downwards at a speed of about 230 meters per second, generating about 89,000 newtons, 20,000 pounds. The total vertical lift of the F-35B, including the main exhaust lift fan and auxiliary outlets, reaches about 175,000 to 180,000 newtons. 39,000 to 40,000 floats exceed the weight of the aircraft to maintain a hovering state. When flying horizontally at a steady speed, the lift fan does not operate. Main engine brush and WSNI F-135 takes over the entire thrust. In vertical takeoff and landing mode, the top cover of the lift fan opens. The coupling connecting the shaft movement and the main engine transmits the force to operate the lift fan under the lift fan. A regulating exhaust helps direct the thrust and the appropriate force of the structure of the aircraft. To reduce the weight, to perform vertical takeoff, vertical thrust from the engine must be greater than the weight of the aircraft. In just under 3 seconds, F-35B can convert 15,700 floats horizontal thrust from the main exhaust into vertical thrust downward to help the total lift reach 39,000 floats. This vertical lift is almost equivalent to the maximum thrust of a fighter aircraft, fight Eurofighter Typhoon. This powerful thrust-generating ability is due to the special engine system of F-35B developed by the company. Looking at the technical characteristics of F-35B, it is clear that this is an ideal aircraft. One point worth noting is the technology of changing the direction of the tail exhaust of F-35B, which, according to information, is said to be referenced from the Jak-141. Is this correct? So why was Jak-141 not mass-produced, although it was shown as a superpower? But the fate of Jak-141 was quite short. In 1991, when the Soviet Union collapsed, the Jak-141 project could not continue and was never mass-produced. Jak-141 is a supersonic fighter capable of vertical takeoff and landing, considered the successor of Yak-38. This is an aircraft perfect in combining propulsion, engine, and fan. However, the development journey of the Jak-141 encountered many major obstacles. The aircraft first flew on March 9, 1987, just over 4 years before the collapse of the Soviet Union in December 1991. At that time, the Soviet economy was in a serious recession, and the Navy, the main orderer, did not have enough budget to sustain the project. As a result, the Jak-141 was canceled in August 1991, when only 4 prototypes were built. However, the story of the Jak-141 did not end there. Of the 4 prototypes, 1 was used for ground testing, 1 for propulsion and structural testing, the other 2 were for flight testing. During testing, 1 prototype suffered a serious accident during vertical landing on October 5, 1991, on the aircraft carrier Amiro Goskov, due to a technical fault technique that caused the plane to crash and catch fire. Although the pilot escaped safely, this incident has reduced confidence in the project. From the above events, we can draw the main reasons why Jak-141 was not mass-produced. First, the technology of the plane was not reliable enough. With a high failure rate, Jak-141 used 3 engines, 1 main engine, Shojak R-79, and 2 RD-41 lift engines forward. When the 2 lift engines start, they produce hot air that can be sucked back into the main engine intake, causing hot air swallowing, leading to reduced performance or engine failure. Second, after the collapse of the Soviet Union, Russia no longer has the financial resources to continue major military projects like Jak-141. Scientists and engineers are in dire straits, not being able to sustain research. Finally, the military, Air Force, and Navy of Russia shifted their focus to conventional fighters, no longer prioritizing vertical takeoff and landing capabilities, leading to the project being stopped altogether. Contrary to the USA's success with F-35B, thanks to superior vision and resources, Jak-141 achieves vertical takeoff and landing capabilities by combining with the R-79 main engine, providing approximately 152 kilotons of power force propulsion with 2 RD lift engines, 41 each, 41.7 kilonewtons during vertical takeoff or landing. The main engine nozzle rotates down about 90 degrees to provide vertical thrust, while the 2 front lift engines operate via intake and exhaust to control attitude and stability. Jak-141 uses air nozzles driven from the main engine instead of separate engines, legs, and thighs. The biggest difference Z-35B and Jak-141 lies in the design. Engine F-35B uses a lift fan connected to the main engine via a drive shaft instead of 2 lift jets like the Jak-141, which eliminates the problem of hot air being sucked back. Although the rotating nozzle of the F-35B bears some resemblance to the Jak-141, there is not only evidence that the U.S. copied this technology directly. In fact, in the early 1990s, Loke Chip Martin paid a small sum, about $385,000, to cooperate with the design bureau, Jacquard, access to the test data of Jak-141. However, this is only a reference activity to improve the X Program 35, predecessor of F-35B, which has been developing the 3BSN nozzle since the late 1980s. The vertical takeoff and landing technology of F-35B is the result of independent research in the U.S., not copied from Jak-141. So are you impressed with the vertical takeoff and landing capability of F-35B? Although excellent, F-35B on ships, aircraft carriers usually perform short takeoffs instead of full vertical takeoffs and landings due to limitations in weight and fuel when carrying heavy weapons. But how can a small runway on a ship aircraft carrier be strong enough to support aircraft takeoff? Currently, navies, countries use 3 main methods to take off aircraft flying on aircraft carriers: skidding, catapult takeoff, and vertical takeoff, of which catapult takeoff is the most common, especially with heavy fighters. Catch-up provides a large acceleration in a short time, helps the aircraft reach takeoff speed on limited runways. catch-up method is currently dominant on large aircraft carriers. The two main types of catapults are water-based and electronic catapults. Recently, China's Fujian aircraft carrier has attracted attention for using electronic catapults, marking a step forward in the country's naval technology. Steam catapults work by using pressure from heated steam to create powerful thrust. On the U.S. Nimitz-class aircraft carriers, each catapult 131 can generate a thrust equivalent to 95 megajoules, enough to launch heavy aircraft such as the F-18 Super Hornet. With 4 catapults operating at full capacity, the ship can put 12 aircraft into the air in about 5 minutes, achieves a success rate of over 98%. This process begins when the pilot puts the aircraft into position. The hook is attached to the tow rope, and the aircraft needs to be secured. The commander controls, adjusts the steam pressure based on the aircraft's weight. If the pressure is too high, the wheels or structure of the aircraft may be damaged. If it is too low, the aircraft will not reach takeoff speed, leading to the risk of crashing into the sea. When ready, the rear hot air shield is raised, the launch button is pressed, and the aircraft accelerates from 0 to about 270 kilometers per hour in 2 to 3 seconds. Then seals, the launch returns to its original position to prepare for the next turn. Steam catapults not only launch fighters, but also support early warning aircraft like the E-2 Hawkeye. Tankers and electronic warfare aircraft enhance the combat capabilities of aircraft carriers. However, aircraft carriers use ski jump runways, like the Russians. Admiral aircraft carriers Kuznetsov or China Liaoning aircraft carrier can only launch light fighters, cannot support larger aircraft due to the noise of the catapult. Although the efficiency of the steam catapult has many limitations, the system is bulky, weighs about 486 tons, and takes up 1,100 cubic meters on a Nimitz-class ship. It consumes a large amount of steam from the boiler, causing a drop in pressure after about 16 minutes of continuous operation, which takes 20% of the steam of the ship and affect the speed of movement. In addition, it requires complex auxiliary systems such as seawater desalination, high-pressure pumps, and heaters, making maintenance costly. Limited range of launch, force adjustment also makes it unsuitable for light unmanned aircraft. And sudden acceleration with great pressure for pilots. With the continuous development of aviation technology and the increasing demand for regional warfare with high technology, the weight and combat radius of aircraft on the aircraft carrier are increasing, leading to strict requirements on weight and takeoff speed, while traditional steam catapults gradually cannot meet these requirements. Therefore, many countries have turned to developing electronic catapult technology. Electronic catapult technology converts electrical energy into magnetic energy, then converts it into kinetic energy to propel the object to the required speed. Linear electromagnetic motor is the main device providing the motive force, using a powerful electric current to create a magnetic field and propel the fighter into the air. The strength of the electromagnetic catapult is the ability to reduce the size and weight. Unlike the steam catapult, the electromagnetic catapult does not require a large space or heavy weight. With a weight of just under 300 tons and a size of only a few hundred cubic meters, thanks to the electromagnetic catapult technology, the workload of the staff operating and maintaining has been reduced by about 30%. At the same time, the area of the aircraft hangar and the ship has also been saved, reduced to only nearly half of what it was before. The electromagnetic catapult is capable of generating a launch force 20% to 30% stronger than the water catapult, allowing it to launch even bombers. This system can adjust the acceleration according to the weight of the aircraft from heavy fighters to small drones, with an adjustable takeoff weight from 2 tons up to 70 tons and terminal speeds of 50 to 200 knots. Another advantage of the electromagnetic catapult is the smooth acceleration curve, which avoids sudden thrust fluctuations and minimizes damage to the aircraft structure. This system also increases the payload effectiveness of the aircraft by 15% while reducing the burden on the pilot. When performing, this is clearly demonstrated on the U.S. Ford-class aircraft carrier, where the ship can deploy over 300 aircraft takeoffs per day, a 25% increase over the Nimitz class. Equipping the electromagnetic catapult enhances the combat capabilities and weapons carrying capacity of the aircraft carrier. Furthermore, the electromagnetic catapult does not generate as much steam as steam catapults, increases energy efficiency by over 60%. The system also has a faster response once it has been completely cooled. Takes only 15 minutes to launch, while the water catapult needs shoulder drop preparation. This makes the electromagnetic catapult more suitable for information warfare, where the battlefield situation changes rapidly. For drones, when using water catapult, the aircraft is often destroyed. Water catapult has been completely eliminated due to the inability to adjust the launch force too much, whereas the electromagnetic catapult has the ability to precisely adjust the launch force by controlling the input current and frequency, thereby launching different types of aircraft with special solutions for each type. Conclusion: after learning about steam catapult and electromagnetic catapult, you can see the clear difference between these two technologies. Right next, we will explore vertical takeoff and landing technology. Although this technology has its origins in the time of the Second World War, but in terms of modern dynamics, it can be classified into many different types. The first type is helicopter, or main, more accurate, suspended vertical takeoff and landing aircraft. This is the most popular vertical takeoff and landing technology currently used in rescue missions, cargo transport, and other special jobs. The second type, as mentioned, are aircraft such as Hawker Siddeley Harrier of UK, Lenzo Jack 38, and F-35B of America. These aircraft are called vertical takeoff and landing aircraft, using jet engines with the ability to adjust the direction of thrust. This name is quite long, so I often call them simply aircraft vertical takeoff and landing. Their common feature is the ability to adjust the direction of the engine nozzle down to create vertical lift, mainly used as fighter aircraft on aircraft carriers. The third type is vertical takeoff and landing aircraft. Propeller technology is more complex. This is a combination of helicopters and fixed-wing aircraft using propellers, which can rotate both horizontally and vertically. This allows the aircraft to take off and land vertically like a helicopter and fly at high speeds like a fixed-wing aircraft using a turboprop engine. A typical example of this type of aircraft is the V-22 off-. The USRA has been in operation since 2007, and V-280 Varro is being BEO developed with a maximum speed of over 500 kilometers per hour, promising future military applications. The fourth type is the UAV, vertical takeoff and landing. The technology is becoming increasingly popular, especially in the small UAV sector. UAVs can accept higher technical risks and are more flexible in design, opening up opportunities for the application of this technology for both military and civil. Looking to the future, vertical takeoff and landing is not limited to the military, but also promises to revolutionize urban transport with flying car projects like Lilium or Joby Aviation. This technology can create three-dimensional traffic space, reducing city congestion. A notable example is Nissan Rover's eVTOL concept announced in 2001-8. This design proposes 6 electric motors combined with gas turbines to charge batteries, reach speeds of around 400 kilometers per hour and a range of 800 to 1,000 kilometers, utilizing existing airports or parking lots. Although Rolls-Royce is now focusing on all-electric, hybrid ideas still have potential. What do you think of the prospect of flying straight home without traffic jams? Finally, vertical takeoff and landing technology will certainly continue to develop in a smart way. like the advances in UAVs today. There is still a lot of potential to improve the reliability and safety of this technology, and we will see big strides in the next decade. Biggest strength: F-35B can take off even without a long runway. This completely changes the landscape of warfare. Japan's decision to upgrade Izumo into a light aircraft carrier is taking naval defense to a new level. But without the which technology is perfect vertical takeoff means limited payload, high maintenance costs. Technical reliability is controversial. F-35B has also been questioned with a high accident rate. But as history shows, strength lies not only in weapons, but also in determination, ability to learn, and the courage to change. That is why Japan, England, Mexico, both continue to pursue this path. Question for you: will vertical takeoff technology become the new standard of naval aviation in the 21st century, or is it just a temporary test step? If you find this video valuable, don't forget to like, subscribe to the channel, and share your thoughts below. My name is Hai. See you in the next video.